Good morning, welcome to Freeburg's Free Advice. We're going to take a look at some calculus today. More specifically, we're going to be taking a look at how objects move and can we use a function given to then help us with determining the velocity and acceleration. And then we're going to kind of tie it all together so you can see actually how all those pieces start to fit and hopefully start to make it make more sense as well. So we're going to take a look at an object that's moving some distance away from a point. We're going to call this some function of t, where our f of t will represent distance in feet, and t will be time in seconds. So we're going to take a look at our function here. We're going to say that f of t equals t cubed minus 12t squared plus 36t. So one of the things I kind of like to do is, even before we start looking at the questions, what does this thing even kind of look like? Well, if we start to just identify the fact that this is a cubic function, and if we look just from time equals 0, we see that this has an x-intercept of 0. So in theory, we've got, we go through the origin here. So hopefully we know that we start there. It's got some cubic behavior. And so we know the end behavior, and at some point this may have a couple humps to it or something like that, right? And so it may look something like that, and so we know that we're going to be moving forwards and moving backwards, or left and right, depending on how you think about it, or positive, negative velocity. And then we'll be able to identify where those turnaround points are by identifying where the velocity starts. So let's look at what is the velocity of the object. Well, as we go across our curve here, we hopefully in calculus have identified that we can find our tangent lines and identify where basically the slope of our curve is, which, if you talk about the change of distance, what you're looking at is your velocity, right? Velocity is the change of distance over time. So if I find that first derivative, we're actually going to be able to figure out what the formula for our velocity is at any given point. So we're just going to go ahead and take our explicit derivative here of the function. So we'll do that f prime of x. And if we don't know how to do that, there's lots of other videos that you can find to kind of talk about it, but really quick recap. Without all the explanation, you're looking at multiplying your exponent here by the lead coefficient, and then we're going to reduce this one by 1 power. So this becomes a 3t squared minus 24t plus 36. And so now we have a function that's going to identify what the instantaneous rate of change, or our velocity, is at any given point during this curve or the movement of our object. So what is the velocity at 3 seconds? All you really need to do is plug in 3 for our x value in our velocity function. And so instead of f of x, we're going to have our f of 3 on this prime here. And so at 3 seconds, we'll see that it's going to be 3 times 3 squared minus our 24 times 3 plus 36. Excuse me, that's a terrible plus sign. And so as we work through our math on that, we'll end up with our 27 minus, that's going to give us 72, plus our 36. And so we'll see that our instantaneous rate of change, or the velocity at 3 seconds, is actually negative 9 feet per second. And so if we look somewhere around here, we would expect that if this was, let's call that roughly 3 seconds, we would have some negative slope here, and we'd see that we're moving backwards. Or if we're considering positive velocity moving towards the right, negative towards the left, at this point we're moving left. We're going back towards the home. Okay, so when is the velocity, we're going to actually go to C here. When is the object's velocity 0? Well, we can then figure out, I want to find those points up there, right? The ones at the very top. And so the tops or the bottoms. And when we go and do that, all you're doing is you're plugging in 0 for your velocity. And so if we plug this into our function we found for velocity, 3t squared minus the 24t plus 36, we're going to just be able to factor that. Well, you can factor it right away, but that's going to give you really big numbers. So I see that 3 is common. I'm going to pull that out early. So I'm left with smaller numbers. So we got this 8t squared minus 8t, or sorry, t squared minus 8t plus 12. Now I see that that's much easier to factor. So we've got this 3 times t minus 6 and t minus 2. Okay, if you want more factoring, actually that's the other video I have posted right now is our factoring. Go check that out. You want to see what's going to multiply to the c or ac and then add to your b value. So here, using our zero product property, we can see that our t values are going to equal either 2 seconds or 6 seconds. So now we've basically found these 2 points up here. So we've got 2 seconds and 6 seconds. Right now that graph I've got, it's not the scale. We'll come back to that here in a second. But we're starting to see some of these pictures that are helping us figure out what's actually going on with the object. Okay? So when is our velocity positive? When is it negative? When are we going left? When are we going right? And so use this information we have. We know that we're going to be moving with a positive velocity. Let's call that towards the right for the first 2 seconds. So if we want, we can go ahead and say that our t in interval notation here is going to be some element from 0 when we start moving at 0 seconds to 2 seconds. So I'm going to be moving towards that right, have that positive velocity. And then we also see that I'm going to get towards the bottom here at 6 seconds. So I'm going to start moving back to the right again when I am 6 seconds or greater. Okay. So technically this would be for infinity, but we'll cap this off at 8 seconds later on. So when am I moving towards the left then, or have this negative velocity? Well, our negative velocity then is going to be an element from, we're moving negative kind of through that piece, right? So we're looking from 2 seconds to 6 seconds. So now we're starting to see what's going on. We have this left-right movement, and velocity is helping us, and we did that all with that first derivative. Okay. Well, let's see what else we can do with it. Okay, so what's the total distance traveled? Well, that's going to actually require us to start to figure out how far did we actually go. So we realize we're going left, we're going right. So we can't just find our starting point and our ending point, because that's just how far we went. But more like with your car, if you're driving, let's say, to the bank and then to a store and then back to the bank and then home, you're not driving 0 miles because you started and ended at home. You got all that mileage in between, which is what your odometer is going to pick up and those kinds of things. So let's see what that actually looks like. Well, you know that you traveled towards the right for the first 2 seconds, right? So we're going to go ahead and find f of 2. Where did I get to after 2 seconds? Minus f of 0. Where did we start from? Because we're dealing with distance, we'll have that absolute value. So whether it's positive or negative, we positive distance. And then we're going to add that when we're moving towards the left. So you've got f of 6, because that's when we're moving left, minus our f of 2. Absolute value again. And then we're moving back towards the right from f of 6 towards f of, and we're going to do this just for the first 8 seconds. So f of 8 minus our f of 6. So basically you're going to go back to that original function, and we're going to plug in all of our values that we found with our velocities that helped us change directions, left, right, and we're going to be able to go find those out. So as we plug those values in, we'll see that after 2 seconds we actually were able to travel to 32 feet. So we had 32 feet here, and we started at 0. So we had 32 feet moving towards the right. Then at 6 seconds, we actually see we get all the way back to 0. And again, we were at 32 feet with our, after 2 seconds there. So we moved again 32 feet, but this time it was towards the left. So when we take that absolute value, we're going to end up with another 32 feet. And then we're going to see that after 8 seconds actually gets you back to 32 feet as well. Okay? So minus our 0 feet at 6. So here's another 32 feet. We can add 32 plus 32 plus 32, which gives us a total of 96 feet. Okay, so even though if we looked at just our start to finish, it looks like we only had a displacement of 32 feet because I started at 0 and I ended at 32. But if we look at that curve and we start to wind through it, you actually see you've covered much more distance. So now we see that we've gone a total of 96 feet. Okay, so what's the acceleration of our object? Well, what does acceleration even mean? And one of the things that we probably most common see are cars accelerating, or maybe even gravity pulling us back to the ground, right? I throw an object in the air. Gravity is accelerating it back towards Earth, which is why things speed up and they hit the ground, and when you throw them up, they come back down. So what's the acceleration of this object? Well, you're really looking at what's your change in velocity. And so, similar to what we did with the change of distance over time, we found our velocity. We're going to do change of velocity over time. And so we're going to actually take the derivative of the velocity function, which is going to look like our double prime, right? Oh, not x, we're using t. So we're going to actually take the double prime. And so from our new velocity equation, which was that 3t squared minus 24t plus 36, we're going to do the same derivative rules here. So we're going to get 6t minus 24. And we're going to, sorry, it's like that. And we're going to see that there's our actual acceleration formula, so we can find acceleration in a given point over time here. So that's helpful because we can start to see when does that object actually start to slow down and move back towards, 0. And so you can find when your acceleration is 0. So if I plugged in 0 for my acceleration, I would see that we could add 24 to both sides. And we could divide by 6. So we would see that our t value here is going to equal 4. So at 4 seconds, we're going to actually see that we've had negative acceleration, which is what slowed it down, and then started pushing it back towards the left. And then it's going to have positive acceleration, so it's going to start to slow back down, going left, and turn back around and head towards the right again, which is what we're expecting with that cubic behavior. So now we have lots of pieces to help us graph. We know distances, so we know that, let's go ahead and build a graph for all of these. We've got 8 total seconds that we're going to graph here. And so let's call that 4, let's call that 6, let's call that 2, so 1, 3, 5, 7. Okay, we know we have a total distance traveled of about 32 feet. It's going to be about as high as we go, so let's go to 40 here. And so this would be 20. And again, I wanted to show graphing because I know most of the calculus kids, you guys are probably good at this, but there's a lot of people I work with that they're graphing, even with rough sketches, it starts to get super out of proportion. So try to make yourself decent scales so that you can make a graph that looks at least kind of pretty. So here's a rough sketch graph for us to help us moving forward. So we knew at 2 seconds we were going to have a total distance of 32. So let's call that 32 roughly. Okay. Then we knew after 6 seconds we were going to be back at 0. And then at 8 seconds, back up at 32. Okay. Couple things to note. We realized that this was a turnaround point because our velocity was 0, so this is where we would expect to start to turn around. This was another turnaround spot, so we'd expect to be turning around there. And our velocity, or our acceleration we just found, is going to change somewhere there around 4. So that's kind of where it's going to go from having this starting to make a steeper curve to starting to come back, right? So we've kind of got that piece going. We know that we started at 0, 0. So super rough sketch then. We can say that this is roughly our distance, right? So this is kind of that base f of t, which we think of as our total distance. Okay? Then we want to take a look at our velocity. So our velocity is at f prime. We saw that that was our, and I'll bring this back over just so we've got them over. You see that we have this this velocity. Okay? So it's a square function. I was able to find my x-intercepts. I can go find my vertex also. So velocity was 0 at 2. Velocity was 0 at 6. What we know about parabolas, right, is we're going to have this axis of symmetry through 4. Our vertex should lay somewhere on there. So let's plug in 4 to the velocity equation. So our f prime of 4. What is my velocity at 4 seconds? We see that the velocity at 4 seconds is, I feel like I already did this, somewhere around negative 12, I think. That's what my graph kind of shows. Or we can double check it, right? So 4 squared is going to be 16. So that would give us 48 minus 4 times, so 48 plus 36, 94, plus our 24 times 4 gives you 96, so 96, 48, it's going to be a negative 48, so negative, yes, good, negative 12. Okay, so we're going to be down here somewhere at about negative 12 at 4 seconds for our velocity. And so this kind of helps us. And we also know that when I looked at our y-intercept here is going to be 36. So I can plot that point roughly there. Okay, at time 0, our velocity is positive 36. Well, with that axis of symmetry, we can also kind of take a look at the mirrored image, right? So over 8 seconds, we should also be at 36. Okay. Now you've got 5 points. This is going to make a nice, pretty looking graph. And so there's our parabola. Okay, so we're starting to get our parabola there, making it nice and round. And so there's kind of a good little sketch, right? So our velocity starts to match up. We see that, oh hey, look, those little peaks and valleys of our distance actually do match up with when our velocity is 0, when I'm changing directions. So that's kind of cool to notice. And then when my velocity is 0, that actually is going to match up with where we had said we're going to have that 0 acceleration. So let's double check and plot our acceleration now. Well, acceleration has a y-intercept of negative 24. So somewhere right around there, slightly off my graph. We said that it had a 0 at 4 seconds, so it's going to go through here. And then, again, this is a linear function, so if I went up 24 over 4, I could go up 24 over 4. So at 8 seconds, we'd be back at 24 feet per second squared for our acceleration. Now, with a perfect straight edge, we'll see that there's our linear function. So you've got all that information tied together now, and it's kind of cool to look at because you actually see that as an object moves left to right, or positive to negative, depending on how you're describing that, you can see where your velocities are 0. You can see where the velocity is changing directions and going from positive to negative or negative to positive, which matches up with your acceleration. So all these pieces start to tie together, and it kind of makes math cool. So I think that's kind of a fun one. It's a little bit physics-based, which is more applied mathematics. I like that. But it's at that calculus level because you're doing those derivatives and looking at instantaneous rates of change. So Hope you enjoyed it. Thank you for watching Freeburg's Free Advice, a little math edition. Have a wonderful day.